Hello, everyone. This is John Crane from MCS&T and Chad Miller from the JF Allen Company, the co-chairs of the Asphalt Joint Subcommittee, and we're going to talk about the new changes to the 401 density specifications as they relate to lot-by-lot testing and roller pass testing. Chad Miller is going to step in and kind of go over all the specification changes, or not all of them, but most of them. And then I'm going to come back and talk about the statistics and verification process, and then we'll have an open discussion at the end. So here's Chad.
Yes, we'll be going through a brief slideshow, going through the forms, filling out the forms, an overview of the specifications, and things like that. Our objectives today is the overview of the new supplemental specification. We're going to be going over the process for gauge comparisons. We'll be doing lot by lot, going over the random locations and how we're going to be doing that. The contractor quality control and the acceptance testing, and the Department of Highways quality assurance and verification testing. We'll also be talking a good bit about the roller pass method, and the reference materials that we'll be looking at are the MP 401-0520 and the new section 401 in the 2019 supplemental specifications. This presentation is dealing with the Troxler 3400 series gauges, talking about the K factor later on. The 3400 series gauges from Troxler is the majority of what contractors and DOH and consultants are using out there. If there's another gauge, another gauge type, we'll have to refer to the operations manual, the owner's manual, to determine how to deal with thin lift corrections on those gauges. For the Troxler gauges, we're looking to standardize everything, and we're wanting the gauges to be facing with the handle towards the paver, keeping everything with the gauge positioned with the paving direction as shown here. Our reference materials, like we said, was MP 401-0520. Sections 1 through 8 will still be in effect. Sections 9 through 11 are overruled by the supplemental 401 specification. Our 401 specification, it's going to provide the requirements for determining how acceptance will be made, whether it's going to be lot by lot or whether it'll be a roller pass project, and also describes some of the processes within. Typically, our quality control testing, our test that's performed to allow the contractor to control the material. These tests are not used for acceptance. The contractor is responsible for the quality control even when acceptance tests are not required. For example, the traditional roller passes, the contractor does the roller pass, the DOH observes it. However, this year, for 2019 projects, under the 401 specification, the contractor will now be doing the acceptance testing. Roller pass projects, the contractor is still responsible for the testing while being observed by the district. That part of it hasn't changed. However, the process has changed for these roller pass projects. We'll get into detail on that here in a bit. For the verification tests are performed by the district to validate the contractor's acceptance test. These results are going to be compared, the contractors and the DOH, for statistical similarity. If the verification and acceptance tests are similar, the acceptance tests are going to be evaluated for pay factors at that point. However, if the verification and acceptance tests are not similar, an investigation by the division will be conducted to determine the reason for the non-similarity, and the extent of the difference. After the investigation, the division may elect to take additional verification tests and evaluate those results for the pay factors. So the DOH will have the option to do the testing for pay if non-similarity is discovered. For 2019, the big new item is the thin lift correction. The new clear gauges theoretically read 3.5 inches deep, but most of our paving is done with thinner lifts than this. The thin lift correction is going to compensate for the existing surface densities. The thin lift correction is going to be performed by the contractor on both lot by lot and roller pass projects. It's the contractor's responsibility to get this testing done. It's going to be the contractor's responsibility to determine if there are different surfaces that need to be tested on the project as well. For a lot by lot project, the thin lift correction is going to be 10 random wet density tests within the first 1,500 feet of paving. An average of these 10 tests will be used as the existing density value in the correction equation. And then any time that the surface changes, a new thin lift correction will be required. If you're going from a milled surface to a scratched surface, that's a condition change, so you'll need a new thin lift correction on the new surface. Here's an example of the new T401 form that we're going to be using. All of our correction, thin lift correction data will go into this upper third area. This is blown up, and we'll look at where to put our numbers. We're going to assume a project is starting at 0 plus 0, 0. So a 1,500 foot section gives us 15 plus 0, 0. We'll come up with our random numbers for target locations. We'll do the same thing for the offsets, and we'll determine the surface type, whether it's a milled surface, whether it be a scratch surface, whether it's existing concrete, or whether it's an unmilled surface. So we'll go through, we'll gather 10 of our wet densities on the existing surface, and we'll average those together. And for this example, we've come up with 2183 as an existing density on the surface that we're getting ready to pave. For the roller pass, it's similar, but instead of 10 random wet density tests, we're taking 5 tests, and this is going to be in a 400 foot area instead of a 1,500 foot area. This 400 foot area begins 100 foot beyond the transverse joint. We're going to average these 5 tests, and these 5 tests will be used as the existing density in the correction equation. And again, a new thin lift correction is going to be required anytime the existing surface changes. Here's a look at the new 407 compaction form. And again, the data will be in the upper third area of the form. This is what it's going to look like. Starting 100 foot beyond the joint, assuming this project starts at 0 plus 0, 0, our beginning station for our thin lift will be 1 plus 0, 0. We go 400 feet, and that gives us 5 plus 0, 0. We run our random numbers to come up with station numbers to take our test. We figure our offsets. We figure what type of surface we have. We keep that recorded. In this situation, we're going to use an unmilled surface. We find our 5 density tests. We average those together, and for this example, we come up with 2176. Moving into the testing process, we'll look at the lot-by-lot testing. What's new for 2019 with this specification is that the lot is going to be 1,500 feet long instead of 1,000 feet long, which 5 equal sublots will give us 300 foot long sublots. And we're still going the full paving width as the width for the lanes. Our acceptance range is 92 to 97%. It's been increased a percent on the upper end. And we will be doing joint density testing on the hot side whenever we pull a 2-lane road. Go through an exercise here for determining the sublots, testing locations, be a review for most, but the guys new into the industry here, it'll be a useful exercise. We're looking at a 1,500 foot lot. In this example, we're going to be paving 15 foot wide. So our lot, 5 equal sublots. Each sublot will represent 300 feet. And just as a visual reference, there's our 5 sublots within that lot. This lot begins at 15 plus 0, 0. So each sublot's 3 plus 0, 0. So 15 plus 0, 0 plus 300 is 18 plus 0, 0. 18 plus 0, 0 plus 300, 21 plus 0, 0. 24 plus 0, 0. 27 plus 0, 0. And finally, our last station, 30 plus 0, 0. We'll take that, apply random numbers to our distances, and we'll come up with our test locations. Random number of 0.683 by 300 gives us 205 feet. Our beginning station's 15 plus 0, 0. We'll add 205 feet to that, and we got 17 plus 0, 5. Our width, 15 foot wide, multiplied by a random number 4.41, 6.6, that rounds to 7. So we have a 7 foot offset. And there's our first test location. It's the same exercise. Figure the location and offsets for the remaining 4. Site 4.996 times 300 gives you 298.8. You round that up to 299 feet. Add that on to 24 plus 0, 0 is 26 plus 99. Our width, 0.729 times 15, 10.9, leads us to 11 feet. And as before, whenever you get a number that puts you right on the edge, as this one, 0.972 times 15, gives us 14.6. It rounds up to 15, but we're holding a foot off of an unconfined edge. So we'll pull that into 14 feet. So continuing on with the process on the lot-by-lot testing, our acceptance test will be 5 random 1-minute density tests per lot, as described in the MP 712.21.26. We're going to average these 5 tests, and they will become our average density value in the correction equation. And then the new thing for this specification, we have to calculate a corrected density. Again, looking at our form, the center section here is where our density data will be stored. This example, we've got a target of 2477, and we're taking our 5 tests, get our values. We move to our second lot, get our values. Our first lot, we got a 2310. Our second lot, we got a 2245. These 2 numbers will become our average densities in their correction equations. And our form, at the bottom of the form, has our equations in there as well. This is what the equation looks like. Your corrected density is your average density of your new mat minus your existing density multiplied by the K value, and it's divided by 1 minus your K value. As we'd said before, this presentation is dealing with Troxler 3400 series gauges, and this K value is unique to these gauges. The K value is going to be based on the thickness of the new asphalt that's being placed, and these numbers are on the form as well. So moving into our example, we've got 1.5 inches of wearing one. Our 2310 was our average wet density of the new asphalt. 2183 was the average density of the existing asphalt. For 1.5 inches thick, our K value is 0.28454. And then 1 minus K is 0.71546. We'll do our math. Remembering the order of operations, we do the math inside the parentheses first. So we have 2310 minus 621.15 gives us 1688.85 divided by 0.71546 gives us 2360.51. And we do all of our rounding at the end, and that rounds to 2361. So 2361 is our corrected density that we'll use for that lot. 2310 was our average. 0.28454 was our K value for 1.5 inches thick. Our corrected density was 2361. And from this point forward, calculating the relative density is the same as before. You're going to divide that by the 2477, and we come up with 95%. Our lot evaluation, 92 to 97% passes, so this lot passes. Also with this, at the bottom of the form, there's a chart to determine the percent pay for your lot. And for 95 to 97%, we have 102% pay for that lot. Now, as we said before, we'll be doing joint testing on these projects as well. So if we're doing lot-by-lot testing with a joint, it's going to be done on the hot side when the second travel lane is constructed. It's going to be 5 random tests per lot, and we're taking these tests 4 inches off of the joint. That'll be 4 inches from the center line joint to the edge of the gauge. And we're going to average these 5 tests, and that's going to be our average joint density in the correction equation. We're going to calculate the corrected density just the same as what we did for the mainline densities. And we're going to evaluate the lot to determine whether it passed or failed. And remember, our specification range is going to be 90 to 97% for our joints. So we use these numbers. This example, we're going to use 2.25 inches to get a look at a different K value. So our main line mat, we got those values, got an average of 2245. We went through and we've done our joint density testing, 4 inches off of the joint, and got those values. And we'll do our calculations. This will be for the mat. We had 2245. Our existing density on the existing roadway was 2183. For 2 1/4 inches, our K value is 0.12078. 1 minus our K value is 0.87922. We'll follow the order of operations, do inside the parentheses first. Do our subtraction. do our division, and we end up with 2254 as a mat density. We'll do the same thing for the joint. We had 2222, again 2183, 0.1278. Follow the calculations through, remembering not to round until the last step. And we had 2227 as a corrected density for the joint. We'll go back to our form. We'll plug in our corrected density for our mat. We had 2254, 2477 was our target. Divide that out, we get 91%. Our pass-fail range for the mat is 92 to 97, so 91 fails. We look over at the joint, we have a 2227. Divide that by our 2477 target, we get a 90%. But remember, for the joint, a 90% passes. So we failed on the mat, but passed on the joint. To calculate the lot percent pay, we're going to look for 91% in the chart for the mat density, which leads us to 96%. Then we also look up 90% for the joint, which shows that we don't adjust the percent pay from the mat. So we have a 96% pay for that lot. One of the things that's changed is the way the verification testing is being done. It's the same concept as before with the quality control and the acceptance testing. The lot size for both the DOH and the contractor will be the same. We'll have the same station numbers. But the DOH is going to be testing approximately 25% of the lots with a minimum of 2 per project. But as John's going to explain after a while, the DOH has to test multiples of 2. So they'll either test 2, 4, 6, 8 lots on a project. For the verification testing, the districts do not have to do the thin lift correction. We're going to be comparing uncorrected wet densities. We'll move on to the roller passes. What's new for the roller pass is that used to, when we come out established number of roller passes, the technician was finished. But this year we're going to have a proving section. Once you figure up the number of passes it takes for the roller pass, then we've got a proving section to validate that that was the correct number of passes for the rollers. And each day on a project, there will be a new roller pass done. So if you have a project that lasts 3 days, we'll have 3 roller passes for that project. The control section really hasn't changed from the way it has standardly been done. It's still going to be a 100-foot long section, but it has been written into the specification that it starts 100 foot from the takeoff joint. A lot of technicians do that anyway, but now it's written into the spec that we start 100 feet from the takeoff joint. It's going to be broken down into 2 50-foot sublots with 1 random testing location within. We're going to apply 4 passes, take a 1-minute test, mark the gauge location, record the results, record the temperature, and do this for both locations. Then we're going to add 2 more passes and repeat the test in the same spot as the first one. And again, record the results and the temperature. And we're going to compare the second set average wet density to the first set average wet density. And we're going to continue this process 2 passes at a time until one of the following 3 conditions occur. Less than a 5 kilogram per meter cubed increase in the average wet density between one set and the next set. Either one or both of the test locations break over, meaning that the density drops. And if the corrected relative density exceeds 97%, we're going to stop the roller pass. So here's an example of what your roller pass section would look like. You've got a 100-foot long section, 2 50-foot sublots, starting 100 foot into the project. You figure up your random numbers and do the math to figure where your test locations are. We'll measure the density. The roller pass goes on T407 form, which is here. And we're going to be recording this data in this center section here. Here's an expanded view. For this example, we're looking at 1 3/4 inches of wearing. So an 1 3/4 K factor is going to be 0.2194. From the example we had before, our average existing density is 2176. Our control section started at 1 + 0 0, went to 2 + 0 0. The station and offset of both test sites. And we went through 4 passes, 6 passes, and at 8 passes, you'll notice test site number A broke over, went from 2263 to 2253. Although test site B increased, test site A decreased. We have our temperatures recorded, our average wet density, so we're going to do our calculation on 6 passes, which was the number of passes before it broke over. We had 2271, 2176 existing density, the K factor for 1 3/4, and we'll go through the math again. Remember to do the rounding at the end. We had a corrected density of 2298. Our 2298 with our target density of 2485 was 92%. And our roller pass passes, because you must have 92% corrected density for your roller pass to pass. Now that a roller pass is passed, we go into the new part, which is the proving section. It's 200 feet long, and it begins at the end of the control section. 10 random wet density tests. The corrected average of those 10 must be 92% or greater. And the corrected average must be within 34 kilograms of the control section corrected density. So we'll begin at station 200, we'll end at station 400, go through, and we'll take 10 tests. Keep in mind, 10 locations in 200 feet, you've got 20-foot sublots. So these tests are going to be fairly close together. So our average wet density out of those tests was 2265. We'll go through the math. again. And we have a 2290 corrected density. So our average density was 92%, and our 2290 was within 34 kilograms of our roller pass density or control section density. So the evaluation is pass. So the technician will be finished with this unless there's an area on the project that the surface changes. And here's a little flow chart of what the roller pass looks like. You're given a 100-foot start zone. That's just an area that takes into consideration the joint that was milled, takes into consideration the fact that the rollers are getting the joint rolled and getting the area established. So at the bottom, you'll see that you've got a 400-foot thin lift correction section. And we'll go through and you start out your 100-foot control section. If that 100-foot control section passes, you go up, you do your 200-foot proving section. If that passes, then you continue with the established number of passes. If your first control section fails, you set up a second control section. If that control section would fail, then you continue with the number of passes associated with the highest percent density, or something worked out with the engineer in the field. If that second control section passes, then you're moving back into the same process of working with the 200-foot proving section. And if that passes, then you continued with the established number of passes. But on any project, after 2 control sections fail, you revert to the number of passes associated with the highest density. There'll be copies of this flow chart available on the DOH toolbox page that can be printed off. Something that we haven't done as common practice, but with this procedure, with this specification, is the comparison of nuclear density gauges. And it's outlined in 4010520. It's also outlined in the spec. Here's what the form looks like, and it's pretty well straightforward procedure. Identification, verification of the gauges, contractor's gauge, the DOH's gauge. Each gauge does their standard block and makes sure that they're within the 2% range for standardizing. And then we move down and do the repeatability and similarity section. The DOH has aluminum blocks that this is going to be done on. So the contractor would take 5 readings. They'd find their high value, they'd find their low value, figure the range. If the range is within 24 kilograms per meter cubed, gauge is repeatable. That one, this example is 22, it passes. The DOH does the same thing with their gauge. They had a high reading of 1910, low reading of 1890. They had a 20, it passes. So both gauges are repeatable. Now to determine if they're similar, we'll average the 5 readings. For the contractor, had an 1861. DOH, we had an 1899. You're allowed a 48 kilogram difference. These had a 38 kilogram difference, so they are considered similar. So both gauges passed this. Looking forward, there's a chance that the districts may have 3 or 4 projects going on at the same time and don't have the aluminum blocks available. In the event that the district would not have an aluminum block available, gauge comparison can be done on a location of freshly paved asphalt. The that's been compacted and cooled. We'll just mark the gauge location, and both gauges test the same spot, go through the same procedure, take the 5 test, compare the range and compare the averages together and see if they're similar or not. So with that, I'm finished with my part of the presentation. I'll turn it back over to John.
All right. We're going to talk about a little bit about the statistics and the actual verification process that the state will go through. So this is the language out of the new specification of the section 40173 for verification. It's essentially that we will conduct our testing independent from the contractor, and then it specifies the number and frequency that we're to do our analysis with. The way it reads is 2 lots per 8 for both mat and joint density with a minimum of 2. After it went through and everything, it kind of that's just it blown up a little bit. It kind of got a little confusing, I think, but the way it was meant was frequency to be 25% of the lots that were done. You always round up to an even number because, like Chad said, to do the statistical evaluation, we need 2 lots to compare against one another. So down here in the bottom right corner, there's a little example of your total lots that the QC does and how many you should do for QA. So if the contractor is doing 8 lots, you do 2. Anything from 9 to 16, the state will verify 4, and so on and so forth. So this is just a little easier way to look at it. 25% rounded up to the next even number. So in this case, there's 10 lots. So that means they're going to do 4 sublot or 4 QA lots. And then those lots will be evaluated with an F test and a T test for statistics, and at a 95% confidence level. And you do, so in this case, there's 10 lots. So the first, you break it in half and do two sets of comparisons of 2. So in this one, there'll be a comparison with lot 2 and lot 5 for the 10 sample locations for QC and QA. And then there'll be another comparison done on lot 6 and lot 8. Just a little bit about statistics for those that statistics escaped them after they left high school, like it did for most people. The F test is a comparison of variance, which is based on your standard deviation of your data. And the T test is a similarity for means. And when you kind of combine the two, essentially, if you can make bell curves with your data, what the 2 tests tell you is whether or not the bell curves fit over top of one another. Just a visual demonstration, going back to the lots 2 and lot 5. If the states and the contractors come in and do all their test data, then you can do a comparison with all that data. There'll be a digital form that we can fill out, if the button will work to click. Looks similar to this. You can plug in the 10 test data points from the QA samples and the QC samples. And the form will automatically figure out the means, the variances, and all the statistical values. And it'll simply report a pass or fail for each of the comparisons, the average and standard deviation or variance tests. So this is an example for the mat density. It's very similar for the joint density. It's pretty much the same thing. So still 25% of the quality control lots are now analyzed. In this example, where there's 10 sublots, or 10 lots, I'm sorry, but only 5 joint lots, we'll do 25% of 5 rounded up. So we'll do the two analyses with lot 6 and lot 8, and just have one comparison. And that's very similar stuff. Data goes in the 2 lines. The form automatically calculates everything and gives you a pass-fail. The whole form shows both mat and joint densities in one thing. So if you have a lots where you're actually comparing mat and you have to do joint comparisons, you can do it all in the same form, and it'll report all together. As far as results from that analysis, if the analysis proves similar, then we can use the quality control data for payments and adjustments. But if it fails, we'll have a special investigation for the districts to figure out the cause and the extent. And this could be, if there's a differential in the gauge comparisons or something like that, or if one gauge is throwing errors or reading incorrectly. It could be all sorts of stuff. We're kind of leaving it slightly open for the districts, not necessarily to get creative on their investigation, but just a little bit of a summary to go through real quick. For lot by lot, we'll do the thin lift gauge. That will be established in the first 1,500 feet of paving, and there'll be 10 randomly located samples to establish that. Then there's 1,500 foot lots for quality control and quality acceptance. Each one has 300 foot sublots. Those are normal lots. There can be adjustments made in the field if necessary. The joint readings, like Chad said, are 4 foot off the hot side, 4 inches off the hot side, sorry. Don't know if, I can't remember if he mentioned it or not, but there is a note right now on the joint density chart that says the actual penalty structure and the notes associated with that table are to become effective for any projects that are awarded after January 1st of next year. So since we've never done any kind of, not really never, but we've done very little joint density readings on projects of this nature, we're just going to in a data collection mode this year. For the statistical analysis, it's always the average wet densities. Since the state isn't required to do a thin lift correction on their stuff, we're taking average wet densities from both QC and QA and comparing those together. That way that we're, if we're not out there first thing in the morning to grab a thin lift gauge or thin lift comparison, we're not holding up the contractor for a long period of time while we try and get our thin lift correction. For lot by lot, there's a 400 foot section for the thin lift. That's always starts 100 feet beyond where the transverse joint to start is. And there's 5 randomly located samples within that. There's two parts of the roller pass. There's a control section, which is the first 100 feet. Like Chad mentioned, you separate into 2 locations, 2 sublots. You apply 4 passes, and then you do multiples of 2 until one of these 3 situations is achieved. Either you are gaining less than 5 kilograms per meter with 2 consecutive readings. Your material exceeds the 97% GMM, or one of the locations breaks over after exceeding 92%. And then once you figure out your control section, there's a proving section, which is the preceding 200 feet. There's 10 randomly located samples. and that average has to exceed 92% and be within the 34 kilograms per meter. Just as some general things, I don't actually think we mentioned this at the very beginning, but here's the 4 scenarios where that everything has to meet for a lot by lot to happen. Roadway has to be greater than 16 feet. You have to pave at least 1.5 inches. Total thickness. Daily traffic has to be 500 or greater. And then you have to at least pave a 1/2 mile. And that's excluding skip paving. So no, 1/4 mile here, 1/4 mile there kind of projects. The relative density is always calculated off of the GMM from the JMF or the verification, whichever is more recent. And then there's the thin lift correction shall be conducted in the event of an existing material change. Chad mentioned this, just reiterating that if you go from asphalt surface to a concrete surface or milled surface to a scratch or PNL, there'll be a need for a new thin lift. But with that said, obviously have some, engineering judgment involved. If you're doing a 30-foot bridge approachment in the middle of a project, that's kind of pointless to run a new thin lift correction, even though you may be going for a new surface, but it's 30 feet, so a little bit of engineering judgment. That pretty much concludes everything that I was going to talk about. So, yeah. And I don't know if anybody has any questions. As far as there's not really any in the chat, but Vince has a question.
They talked about in verification testing, if they're statistically similar, you're good. If they're statistically non-similar, a special investigation happens. What would be the process during one of these special investigations?
There's not really a set guideline for that, but you first want to make sure your gauges are reading similar. And then it's kind of up to the situation that the projects happen to have to figure out what's going on again. Yeah.
Yeah, I have a question.
They can unmute themselves. Go ahead.
Hello?
Yeah.
Does the gauge similarity test have to be done every day?
I'm sorry. Say again.
The gauge similarity test. Does that have to be done every day?
Just once per project. Yeah, just once per project. Unless you have different gauges on the job.
I think so, just once, unless you different gauges.
Okay, thank you.
John, you've got a handful of questions in the chat box.
So this will be available for those that are asking for it. This presentation and everything. There's a question about whether or not lifts of more than 3.5 inches. The gauge only reads 3 to 3.5 inches, so there won't be any correction factor for all that. So you just do it with the standard practice without the fin lift correction.
Essentially, your K becomes 1.
Yeah, essentially your K becomes 1 and it ignores everything below it.
Will we be able to print this off?
Print this off? Is that what you said?
Yes, the preview you went through, are we able to print that off?
Yes. Yeah, there was a question about whether or not this will be done on purchase orders. If it meets the criteria that are at the very beginning of the specification, those 4 things, then yeah, it would end up being a lot by lot testing.
To clarify the question on paving on stone, those thicknesses still be 3.5 inches or 4 inches. It'd still be no K factor. Hmm. The question about taking the gauge home at night to charge it, that's up to the individual's NRC license and company policies.
I've got another question.
Okay.
What about pre-existing stuff we've already pre-bid? That's, like we bid last year that we're doing.
Then
You understand my question?
Or ongoing jobs.
yeah, the project bid last year won't have.
I didn't hear your answer.
Can you hear me?
I can now.
Anything in 2018 will follow those.
I can't hear you now. Like you started hearing you now. I couldn't hear you.
Can you hear me?
Yes.
Anything that was bid in 2018 will follow the 2018 specifications.
Okay. Great.
So the old lot by lot procedures and roller pass procedures.
Okay, that's what I thought. Just want to make sure.
Okay. Is there any other questions?
I
Okay.
guess the state inspectors are they're going to have the forms available for this.
Yeah, the forms and the flow chart that we showed will all be available on the MCS&T toolbox. So if you've never been to there, you can go to Google and search West Virginia DOH materials toolbox. It should pull straight up, and they'll all be available on there. Digital forms, digital Excel forms you can fill out.
You can fill them out digitally.
Yes.
Awesome.
And then they all have built-in calculations in them as well, so essentially tell you what you got without having to do all the math.
Okay, great.
I'm gonna get a laptop now.
Oh, yeah.
Okay, there was another question about being put in Site Manager. We are going to be entering all this data in the Site Manager. The Site Manager forms aren't quite complete yet, but they will be here shortly. So it'll be the same thing what we do right now for roller passes. I guess there'll just be a few extras of those, and then lot by lot we'll be putting in the QC and QA data. So. Okay, if there's nothing else, you have my email from the invite. If you guys have any questions, you can email me. I don't know if Chad put his information out there or not, but if we can get back with you if there's any problems or any further questions later. Thank you for joining, and have a good one.
Thank you, John.